So today I'm going to go over some of the problems from the first two thermochemistry worksheets and just do some example walkthroughs. You have the mix of answers for the problems at the bottoms of the pages, so you can use that to check. There was one mistake, and it's one of the problems I'm going to do. So if you couldn't figure out one of the answers, that might be it. So I'm just going to do several examples, go through them. If you have any questions, email me or stop by during the Zoom office hours and ask. From what I gather, it seems like most people are doing okay. So first, I'm going to start with the worksheet number 1, energy and heat, and do a simple conversion. So convert 2,000 calories to joules. Notice that is calories with the capital C, and that means it is actually 1,000 little c calories. So I'm going to show you how to set that up. And yes, you don't have to do all the setting up that I'm doing, but it's good to. So you're going to start with, it's a conversion, so 2,000 big C calories over 1. There are 1,000 little c calories in 1 big C calorie. And then our conversion factor to get to joules is 1 calorie on the bottom, because that's what we want to get rid of, is 4.18 joules. So you end up doing the math on that, and you get 2,000 divided by, or times, excuse me, 1,000 times 4.18, which is 8,360,000, or 8.36 times 10 to the 6 joules. So 2,000 calories, which is a standard, 2,000 big C calories, which is a standard diet for a human being. Maybe a little low, but 2,000 to 3,000 for humans are. That's about 8 million joules of energy that we take in every day. So for the next one, I'm going to do number 11. What is the change in heat required to raise the temperature of 200 grams of iron from 20 to 80 degrees Celsius? And I gave you the specific heat of iron as 0.511 joules per degree Celsius. So for all these, Q equals mc delta T. Remember that change in heat, that's Q, that's energy in joules or calories, but we're going to deal with joules. And temperature is how warm or cold something is. Temperature is the effect of heat, but they aren't the same thing. So temperature is those degrees Celsius. Q, or heat, is in joules. So we're looking for what is the change of heat. So we don't have to rearrange this equation at all. We'll just plug in all the numbers. So Q equals the mass, which is 200 grams, times C, which is the specific heat, 0.511 joules per grams degrees Celsius, times the change in temperature. And this is final temperature minus initial temperature. And since it's 80 and 20, I can cleverly in my head realize that it went up 60.0 degrees Celsius. And then if you look at your units, and I'm not going to do this for everyone, but if you look at the units, grams will cancel out, degrees Celsius will cancel out. You'll be left with joules, which is what you want because you want to change in energy. So that's going to equal some number of joules, and we do it 200 times 0.511 times 60 equals 6,132 joules. So 6,132 joules, and that is your change in heat. So that's how much heat you would need to raise 200 grams of iron from 20 to 80 degrees. Glass block has a specific heat of 5.0 or 0.502, excuse me. What would be the final temperature of the glass block if 1,700 grams absorbs 7.11 kilojoules of heat? The initial temperature was 23.2. If you didn't know the initial temperature, you couldn't do this. All you could say is a change in temperature. But what we want to figure out here, again, we're going Q equals mc delta T, we want to figure out the change in temperature. If we know the final temperature, or excuse me, know the initial temperature, we know the change, we can work backwards to figure out the final. So delta T equals Q over MC, and we have these numbers. So delta T equals, now you want to be careful, that's 7.11 kilojoules, and I'm going to convert that to 7,110 joules, because our specific heat is in joules per grams degrees Celsius. So we want to convert our energy into joules. I just multiplied that by 1,000. If you actually want to do the conversion, you certainly can, but you don't have to. I assume all of you know how to multiply by 1,000. So that's how many joules. We're looking for our mass. Well, 1,700 grams. And again, this has to be in grams. If they gave it to you in kilograms, you have to convert it to grams so that the units on the specific heat match up. Times the specific heat, which is 0.502 joules per grams degrees Celsius. So because this is joules per grams degrees Celsius, the other components have to be joules and grams, and we're going to get degrees Celsius in temperature change. So 7110 divided by the quantity, so that means I'm putting in parentheses 1,700 times 0.502 and the parentheses, and we get the temperature change equals 8.33. The specific heat is what's limiting my sig figs. If you wanted to say, well, or the amount of heat it took in, so 3 sig figs. And now we know the delta T was 8.33. That means it went up 8.33. So all you have to do is 23.2 degrees Celsius plus 8.33 degrees Celsius equals 31.5 degrees Celsius. Now, here, because I'm limited to the 10 spot here, remember adding and subtracting it's by decimal place for sig figs, I'm going to 31.5. If you put 31.53, life will go on. So last one. First of all, I want to put some more space here. So specific heat capacity is how many grams or how many joules it takes to raise 1 gram of a substance by 1 degree. Molar heat capacity just replaces that 1 gram with 1 mole. So how much it takes to raise 1 mole of any given substance, 1 degree Celsius. So if we want to calculate the molar heat capacity of water, well, that's really easy to do. We know that water is 4.184 joules to raise it by 1 gram and 1 degree Celsius. Well, to figure out how much you need to do the same thing, you just do x over 18.01 grams times 1 degree Celsius. So the reason I use 18.01, that's the molar mass of water. So molar mass of water is 18.01. And so you solve this by multiplying both sides by 18.01. So 4.184 times, I'm sorry, that should be 18.02. There's 2 hydrogens on water, my mistake. Let me fix that. Okay. And you get 75.40. And that would be, now the proper units for this would be joules per mole degree Celsius. It could be kelvins too. So degree Celsius and kelvins, since it's a change, doesn't matter. So 75.4. Oh, just realized I made a slight mistake. I was going to 4 sig figs here, so I actually calculated, or I rounded wrong. I didn't do anything else wrong. The calculation's all fine. I just rounded wrong. This should be, I believe, 75 point. I'm doing this from memory, but it's, I believe, 3.6 was what it was. So I should have 4 sig figs. I don't know what I was doing. I was thinking 4 sig figs, but then I rounded to 3 and put a 0 on the end. So, my brain's starting to go. It happens. Okay, so that is worksheet number 1. Uh, if you have any questions, again, feel free to email or ask at another time. Now I'm going to go to worksheet number 2 really quick and do one calorimetry problem and a couple thermo equation problems. I did some examples of calorimetry problems in the previous video, so I'm not going to do it. I'm just going to do one of these. A piece of ice is placed in a calorimeter with 50 milliliters of water at 81.4 degrees Celsius. The temperature of the water drops to 2.5 degrees Celsius. What is the delta H of the ice? Remember, delta H and Q can be used interchangeably. There are more advanced technical differences, but for the most part, they can be used interchangeably. The thing you have to remember here, we're doing Q equals MC delta T. But generally, we're doing Q of the water, and then equals negative Q of the system, whatever we're interested in, because the water is going to be our surroundings. So we're always going to find out the change in heat in the water, and then we're just going to flip the sign, and that will tell us what the change in heat of whatever it is we're interested in happens to be. So if we have the piece of ice at 10 degrees Celsius, well, that fact that it's at negative 10 degrees Celsius doesn't matter for our calculations. We need to find Q of the water. So Q H2O equals the mass, Q equals MC delta T. So the mass of the water, which is going to be 50.0 grams of water. Again, water, we assume 1 gram per milliliter. That's the density of water. So C of water is always going to be 4.18 joules per grams degrees Celsius. If you happen to do 4.184, that's fine. I usually round it to 4 spots, or, well, 4 sig figs, but the book does 3, so I've kind of tried to transition. But 4.18 and 4.184 will give you very slightly different answers. Either one would be fine. If the rounding's a little different, I would never have marked that wrong. Okay, so that's water-specific heat. And now we just need to figure out the temperature change. Well, temperature change, delta T equals final temperature TF minus initial temperature, delta T equals the final temperature, 2.5 degrees Celsius, minus 81.4 degrees Celsius. Ran out of room there for the degrees Celsius. But we will see that delta T equals some number that I'm going to figure out on the calculator. And the delta T is negative 78.9. And the fact that the delta T is negative makes sense because the water got cooler. Be it cooler, delta T is negative. So now we just plug all those numbers into a calculator to figure it out. So Q H2O equals 50 times 4.184, or excuse me, 50 times 4.18 times negative 78.9, and you end up with negative 16,490. So 490, and because I am working with sig figs here, and I have 3 sig figs here, and 3 sig figs here, and 3 here, I'm going to go to negative 16,500. 490 would round to 500. So that's the Q of the H2O. Shockingly, the Q of the iron, or Q of the ice, excuse me, not Q of iron, the Q of the ice would be the opposite of that. would be positive 16,500 joules. And all that means is that that ice took in 16,500 joules, or 16.5 kilojoules if you prefer to give it that way, from the water. Okay. Now I'm going to talk about thermochemical equations, because these can be sort of complicated if you don't know what the question's asking. So these questions are all worded in a specific way. This is the way they're really worded, how people really talk about them, but I understand they aren't all easy to understand on first go through. So I'm just going to go through a few of them. They're very simple once you understand what you're looking for, but just make sure I go through so you guys know what the heck it's talking about. Otherwise, it could be a little confusing. So, thermochemical equation for the combustion of sucrose is below. What is the heat of reaction, delta H of reaction per mole of sucrose? Well, so delta H RXN overall is going to equal, this is for the whole thing, not per mole of anything, is just going to equal negative 2.226 kilojoules. The reason for that, if kilojoules is written as a product, that means it's being given off. That means it's exothermic. So when we write heats of reaction, it gets the negative. The negative indicates that heat is leaving, and so that's what we have. So all we're going to do is take that number, per mole H2O will be 2.226 divided by 1, or sorry, not per H2O, I'm going to start with sucrose. Per sucrose, pen here, C6, or C12, sorry, I think in glucose, H22, O11. It's just that divided by 1, which is negative 2.226 kilojoules per mole of H2O. It'll just be the overall reaction divided by 11, because water has 11 moles in this reaction, or you produce 11 moles of water every time you make this much heat. So negative 2,226 divided by 11 equals negative 202.3, not 2.023. So negative 202.3 kilojoules. So per every mole of water that's made, you're going to get 202.3 kilojoules of heat. So all you're doing is taking the overall heat of the reaction and dividing it by the number of moles in the balanced equation. Of course, all these equations have to be balanced. Thermochemical equations are written for the balanced equation. Okay, so the next problem I'm going to do is number 8, and I believe this is the one where I messed up the key. We'll come back and do number 5 in a second. Because I messed up the key, I just wanted to get this one in. So, what is the heat of reaction, or what is the enthalpy change, delta H, for 1 tablespoon, 14 grams of baking soda, when it decomposes in the so-called pancake reaction to form light, fluffy, tasty pancakes? So this is the real reaction that happens with baking soda to make like pancakes. That's why we use baking soda in things like that. It'll decompose into, among other things, CO2, which will cause the little bubbles that make the pancakes fluffy. So here's how we do this problem. First, we got to figure out how many moles of baking soda we have. So we're starting with grams to moles conversion, which is fairly simple. 80, excuse me. I want to start with the 14 grams were given. So 14 grams NaHCO3 over 1, and then the molar mass of baking soda, or sodium bicarbonate, is 84.01 grams per 1 mole. And that will give us the number of moles we have. So 14 divided by 84.01, and we get 0.1667. And that's to 4 sig figs because our grams was 14.00. Moles NaHCO3. So that's how many moles we have. We also know the delta H of this reaction equals 129. That's a terrible 9. 129.0 kilojoules. So every time you want to do this reaction as it's written, you need 129 kilojoules. And that is for 2 moles of baking soda. But we don't have 2 moles. We have way less than that. So if you need 129 for 2 moles, how much do you need for 1.667 moles? So all we're going to do is, and there's a lot of ways to set this up. I'm going to take this, and I'm going to use it as a conversion factor. So I'm going to say, I'm going to take our moles and use it as a conversion factor. I'm going to convert moles to kilojoules. So I'll show you how I do that. Change the color here to red. So 0.1667 moles NaHCO3 over 1. And we actually have a conversion factor between moles and kilojoules. That's what the heat of reaction gives us. We know that there are 129.0 kilojoules used for every 2 moles of NaHCO3. And it's a weird conversion, but it's a conversion. It works. We have kilojoules and moles in the same instance, so we can do that. 0.1667 times 129, and then divided by 2, and you get 10.75. And that'll be kilojoules. So you need 10.75 kilojoules to make pancakes with 14 grams or a tablespoon of baking soda, or at least to decompose the baking soda part of the pancakes. That was, I think that's the one that was like 11.28. I think I changed the conversion from 15 to 14 grams. I could be wrong, but that is the correct answer, 10.75. So that one is not on the mixed up answers. Sorry about that. That is my mistake. It's not the first one I made, nor will it be the last one. So I'm going to go back really quick and do number 5. So number 5 says, what is the delta H for the production of NO2 if 95 grams of NO2 are formed? So again, this is going to be, we're going to put grams to moles, so 95 grams of NO2 over 1. NO2 has a molar mass of 32 plus 14 is 46.01 grams NO2 over 1 mole of NO2. And then, and I'm just going to do this straight as a conversion, we happen to know, so the delta H for this reaction is negative 28.57 kilojoules, because it's negative because it gives it as a product, so giving off the heat. We know that's for 2 moles of nitrogen dioxide. So we're going to convert moles. We'll put 2 moles NO2 on the bottom and negative 28.57 kilojoules on top. And I did this whole thing as a conversion. I actually can cross out my units. And it's weird, but it works. Grams of NO2, moles of NO2, and you end up with kilojoules. I'm going to get rid of those cross-out marks so you can better see the thing. I don't know why I did that. C, Control C. Okay. So if you do the math on this, 95 divided by 46.01 times negative 28.57 divided by 2, and you get 290 negative, and I'm going to round to proper sig figs here, so you got something very slightly different. It's rounded sig figs. You'll get negative 2,950. You should put a decimal point after that for sig figs. Or I'm sorry, no, you don't need a decimal point. It's 3 sig figs. Negative 2,950, and that is the unit you have left, which is kilojoules. So there you go. There's a walkthrough of several of those problems. I hope that helps. Again, any questions, ask me. I'm pretty sure all the other mixed up answers are correct, except for that number 81. Down here, it's 10.75. It's not, I think 11.28 is what I had on the sheet. Okay. Have a good day, Jeff.